Good morning everyone. This is the PPT of digital signal processing subject. My topic is about real-time signal generator for noise radar. I am G Naresh from ECE section, IARE College. Let's get into the topic. Introduction. Noise radar is a type of radar system that uses random or pseudo-random waveforms as a transmitter signal instead of traditional sinusoidal waveforms. The noise waveform allows for higher bandwidth and lower peak power, which can improve radar performance in certain scenarios, such as through wall imaging and target recognition. However, the use of noise waveform also requires a specialized signal generator that can produce this waveform in real time. A real-time signal generator for noise radar is critical component in the noise radar system, as it is responsible for generating the noise waveform that will be transmitted by the radar antenna. The signal generator must be able to produce the waveform with higher accuracy, as any derived from the reserved waveform can result in regarded radar performance. Additionally, the signal generator must be able to operate in real time, meaning that it must be able to produce the waveform at the required speed to meet the radar's update rates. A real-time signal generator for noise radar can be designed using digital signal processing DSP platform such as a field programmable gate array FPGA or digital signal processing chip. Here are the general steps to design a real-time signal generator for noise radar. The steps are: determine the specifications of the signal generator such as frequency range, bandwidth, and output power. Use an appropriate DSP platform such as FPGA or DSP chip based on the requirement of the signal generator. Design the signal generator algorithm using the noise waveform such as pseudo-random noise sequence, PRN sequence, or the binary phase shift keying BPSK waveform. Implement the algorithm on the chosen DSP platform using the high-level programming language such as Verilog or VHDL. Test the signal generator in real time using the noise radar system and adjust the parameters as necessary. Verify the performance of signal generator using appropriate metrics such as signal to noise generator or range resolution. Optimize the design for power consumption and size if necessary. FPGA Field Programmable Gate Array Implementation. Our real-time signal generator is created by combining PRN and CPRN generators. The PRN generator is able to generate samples with waveform, Gaussian, exponential, and delay distributions. The CPRN generator block generates colored pseudo-noise samples with the inverse FFT, inverse Fourier transform method. Outputs of these two generators are switched through the multiplier and routed to the pulse generator block, which PRN generates continuous and pulse signals. Also, the pulse repetition frequency of generator signals can be adjusted as constant, stated, and random values. Finally, the controller block provides peripheral component interconnect express based control signals from the host PC for controlling and selection of the distribution parameters and can transfer digital noise samples to the host PC. The details regarding the main block, PRN, and the CPRN generators are presented below. This is a block diagram of FPGA Field Programmable Gate Array. As mentioned in the topic, the PRN and the CPRN both outputs are given to the multiplier, and then the multiplier output is given to the pulse generator, and the output is taken at the DAC. PRN generator The PRN generator. The PRN generator is designed by improving our previous work based on the Box-Muller algorithm. The capable of generating uniform normal, relay, and exponential distributions. The main block diagram of design is given in the figure. The uniformly distributed samples are generated by 32-bit Tusworthy RNG blocks. Each block uses the Tusworthy noise generator method, with provides better randomness with the lower resource utilization. The Python code for the 32-bit Tusworthy generator is given the figure. The use of two Tusworthy RNG blocks is necessary for modeling of normally distributed samples with the Box-Muller method. No uniform samples with the 48-bit can model the normally distributed samples with 8.15 sigma. In the ideal case, this value must be infinite, and to implement generated samples depends on the value and increases within it. To implement square root and ln of and sine cos functions piecewise polynomial approximation is used in this method. An approximation of an f of x generator is transformed into y, which is second step. The approximation of f of y function in a dash and b dash intervals is obtained by the equally dividing the a dash and b dash interval and calculating the Cn coefficient for the polynomial equation that is given to the following equation: y of f of y is equals to Cn into y plus Cn minus 1 into y plus so on plus c naught. The sample Python function for generating the Tusworthy samples is the code is shown in the figure. Due to the symmetry of the sine and cos functions, only the first quarter period of the cos functions with the first order polynomial equation is approximated and used for the other quarters of the sine and cos functions. For sine and cos functions, the lookup table methods can be also be used, which could be faster, whereas due to the minimum area considerations, polynomial approximation is chosen after realizing the required functions for the Bloch-Muller algorithms. Gaussian distribution samples are obtained by using x square and square root blocks in the figure. Square root of the sum of squares of the Gaussian distribution samples are taken and Linear distribution samples are obtained if v is equals to 0, else Lyson distributed samples are created. This is the block diagram of PRN pseudo random number generator block diagram. CPRN generator. This block diagram can generate noise samples with Gaussian PDF and uniform PSD. Amplitude generator block is designed to generate the relay distribution samples. The same Bloch-Muller structure of the relay distribution samples in the PRN block is used for the block. The phase generator block is used for generating the phase samples that are independent of the characteristics of the amplitude and the frequency samples. These samples must have uniform distribution and are generated by using Tusworthy RNG blocks. Amplitude and phase samples are used for obtaining the real and imaginary inputs of the IFFT. If we represent these values as IFFT real and IFFT imaginary respectively, they can be calculated where n is the length of the IFFT and a is the amplitude and f is the phase with the sine and cos functions. Therefore, IFFT real is equals to n by 2 into a into cos pi, and IFFT imaginary is equals to n by 2 into a into sin pi. The frequency generator block generates uniformly distributed samples for a defined uniform frequency interval to generate noise samples within the defined frequency range. The FFT bin in the IFFT blocks must be fed according to the following equation. IFFT bin is equals to Fi into Fs by N is equals to Fi by N, where FS cancels, where IFFT bin is correspondingly frequency bin number. Fs is the sample frequency, Fi is the generator frequency, and this PPT presents the design of real-time pseudo-random number generating for the different probability distributions. Also normally distributed samples with the uniform power distributors have been generated. This design can be used for testing noise and detection performance for the different noise distributions. This is the different noise distributions, and the simulation results for CPRN generated based on samples. Colored noise samples B, and the C is the colored noise samples. Our future work will be of the design of the noise radar simulator by adding a receiver correlator matched filter structure to the noise generator design with the radar target generator. Designing a real-time signal generator for the noise radar requires a deep understanding of digital signal processing as well as expertise in hardware design and testing. In particular, a field program gate array FPGA or a digital signal processing chip may be used as the hardware platform for implementing the signal generator algorithm. Overall, the well-designed signal generator is crucial for achieving optimal noise radar performance and unlocking the full potential of this promising technology. Thank you.